Hi everyone, I'm Minchen from Hong Kong University of Science and Technology. I'm here to present our work Gillis, which is designed to serve machine learning model inference on serverless cloud. Machine learning serving is to deploy a trained model for users' requests. It usually has highly dynamic demands and have stringent SLO on latency. In that case, the inference service in the cloud needs to be highly scalable, meet latency SLO, and cost-effective. Among existing cloud services, the newly emerged Service Cloud is well suited for hosting machine learning models. First, it's easy to use. Users just write cloud function and leave all the server provisioning to the cloud provider. And it's also highly elastic compared with VMs or containers, as functions have much shorter startup latency. In addition, it is cost-effective due to its fine-grained and pay-per-use billing. In summary, given the dynamics of inference workload, we can simply deploy models as cloud functions to enable highly scalable and cost-effective inference services. However, existing service platforms only have limited resources. For example, in Google Cloud Function, each function instance have only up to 4 GB memory and around 300 Mbps network boundaries. The limited resource can make Cloud Function inefficient to serve large models. To show this, we execute a wide ResNet on two popular service platforms, AWS Lambda and Google Cloud Function. For wide ResNet, the wider model has larger size. As we can see, the larger models usually have longer latency and could violate the latency SLO. And functions cannot host some very large models due to out-of-memory errors. To address the resource constraints, there are mainly two approaches. The first is model compression that creates a smaller model. However, this approach usually results in reduced accuracy and requires model retraining. A better approach is model partitioning that enables parallel execution without accuracy loss. However, existing partitioning techniques cannot directly apply to service functions. Next, we will show the challenges of service-based partitioning. The first challenge is to coordinate service functions. Normally, model partitioning requires multiple workers to synchronize their computations, which is straightforward when workers are addressable. However, functions are unaddressable and they cannot directly interact with each other. The second challenge is about the communication. Parallelizing a model requires transfer tensor data across multiple workers. Due to the limited network boundaries, it could incur significant communication costs. Third, while the existing model partitioning techniques either focus on model training or model serving in edge, service-based inference serving has different targets, which aims to meet the latency SLO and minimize the serving cost. To address the challenge, we propose Gillis that can automatically partition the model across multiple functions. This figure gives an overview. In Gillis, we have performance model to predict the inference latency. With the performance model, we have two partitioning algorithms to minimize the latency and minimize the cost with SLO compliance, respectively. After performing model partitioning, Gillis can deploy partition as functions, and it supports multiple platforms, including AWS Lambda, Google Cloud Functions, and Kinix. We next illustrate some details about how we address the aforementioned three challenges. Since the function has no stateful connection, we coordinate functions with fork join process. That is, to serve an inference request, we have a master and multiple worker functions, where the master triggers the workers using RESTful APIs. Each worker computes its partition and returns the results to the master, which can then assemble all the results and process to the next round. For the communication, existing partitioning techniques usually perform layer-wise parallelization. That is, parallelizing individual layers. For example, the input layer, the input tensor to a CNN layer can either be parallelized by the height and width or by the channel dimension. This approach can lead to high communication cost in our server settings. Therefore, we apply cross-grained parallelization that combines multiple layers into a single group. For example, the first two layers L1 and L2 can be grouped as their inputs are locally related. parallelizing the whole group can reduce the communication overhead compared with layer-wise parallelization. While layer grouping can reduce the communications, it may cause redundant computations, as some convolution-like operators can result in an overlap in their interpartitions. In that case, we need to balance the communication overhead and computation cost in partitioning. Next, I will briefly introduce our two partitioning algorithms. The latency optimal algorithm aims to minimize the inference latency. We use dynamic programming to find the optimal strategy. In this equation, we recursively compute the optimal latency of the given model by varying the number of layers and the memory budget. The SLO algorithm is to minimize the inference cost while meeting the latency SLO. Unlike latency optimal, it requires searching over all possible partitioning strategies to find the optimal one, which is infeasible for large models. We thus turn to reinforcement learning-based algorithm. In particular, we designed a hierarchical RL model to learn the optimal strategy. It has two agents, the partitioner and the placer. The former determines how layers are grouped and parallelized, and the latter determines how partitions are placed. After generating the execution plan, we get the latency and the cost from the performance model and compute the reward using this function. In summary, in Gillis, we have three solutions to address the challenges. We coordinate the serverless functions with Jiang and apply cross-grain parallelization to reduce the communication cost. And we propose the RL-based algorithm to minimize the cost with SLO compliance. We have evaluated Gillis with multiple models on three serverless platforms. We first show the results of latency optimal algorithm. We compare this algorithm with the default serving, which uses a single function to serve a model without parallelization. This figure shows their inference latency, while Gillis can achieve great latency improvement for all the models. In particular, the latency speedup for VGG16 is about 3 times. We next evaluate the SLO-aware partitioning. Here we compare our algorithm with another learning algorithm, Bayesian optimization, which is usually used to optimize a black box system. The left finger shows the latency and the right finger shows the cost. In comparison, our algorithm can always meet the latency SLO and reduce the cost by up to 1.8 times. This shows that the RL-based algorithm is better suited for our problem. We have open source Gillis in GitHub. Feel free to contact me if you have any question about Gillis. Thank you for your attention.